He is starting to and has already made a name for himself in this relatively new area of computational metallurgy. I think it's a new frontier in research, and he has the interest of a lot of companies who are very much enthused by the outputs that he's created. I'm going to leave Tom now to begin his talk. Just so as you know, we will be taking questions through the chat and through the raised hand system at the end. And I'm sure there'll be many questions that you have for Tom at that point. So I'm going to pass over to Tom, who will share his screen and begin the webinar.
Brill, thanks very much. Rising star, I think that's the nicest thing anyone's ever said about me. So thank you very much. So hopefully I'll share my screen and this will work. So maybe Brill. Yeah, so thank you. Thanks very much for having me. So I think it's worth saying before we get going, there's going to be a bit of maths in some of these slides, and it's not to sort of be intimidating or anything. I think sometimes it's just useful to say what we do differently at Manchester and in our group compared to what's maybe done. There are a lot of these similar tools or something that does something in the same area might be available in a commercial product, but obviously we're exploring these new areas, so we have to develop our own new mathematical tools and numerical implementation. So please don't be put off by the maths. Hopefully I'll just be using it as a way to explain what we've been doing and how it's new and how hopefully it can benefit sort of industry and also other academic researchers. So yeah, a lot of people use the stuff we've done, and I'll speak about open source stuff a little bit. Yeah, so broadly speaking, the talk's gonna be broken up into three sort of areas. So yeah, we do a lot of work in a lot of different areas and we I didn't include everything on this talk, but broadly speaking, the work that we do in our group in terms of the modeling is divided into sort of the when materials in the fluid state, so in the liquid and vapor state, and then also we do a lot of work in the solid state. And basically my work is mostly interested in materials going through state transitions. So normally if you apply a high energy density source, you'll initiate a state transition that might be solidification or melting, solidification, vaporization, condensation. Also, you can get microstructural changes due to high energy density load. So you can get coarsening of grain structures or shock propagation and fracture formation in microstructures. So yeah, there's sort of three areas, but actually, hopefully, you'll see by the end they're all kind of one family of work. So continuum mechanics is the area I sort of work in, and that's sort of all areas of continuum mechanics. And my research, as I say, is broadly broken up into these two areas, sort of things in the solid state, things in the fluid state. But obviously, and it's all one system of equations at the end of the day, but also work quite closely with experimental colleagues. So, and again, hopefully you'll see in this talk that all of this stuff is validated either by analytical solutions or experimental measurements. So yeah, work very closely with my experimental colleagues. So then that being said, then the first thing I wanted to talk about is the work that we've been doing in the fluid state, the sort of thermal fluid dynamics work that we do. So this is work that's particularly relevant to welding and joining, I guess. So if you're in the metals foundation industry sector, I guess this is work that would be of interest to you. So anything to do with welding, joining, solidification. This is the kind of work that we've been sort of successfully deploying with a lot of industry partners. And basically just a little bit of math before we get going. So if you have a metal and you apply a high energy density source of heat, that might be through a laser beam or an electron beam or electric arc, then you melt the material, and there are a lot of quite interesting physics that's going on. So often when people try and describe these systems mathematically, there's often some simplifications you can make. So the main one is that the flow is incompressible. So that mathematically, if you want to say something's incompressible, you say that the divergence of the velocity field is zero. So that's this little upside down triangle. The dot product with the velocity field, which is u, equals zero. And what that means is that for any parcel of fluid, the amount of fluid flowing into that region is equal to the amount of fluid flowing out of that region. And That's all very well and good if you've got fluids that are behaving in that manner. But actually, what tends to happen is people use that simplification for fluids that aren't behaving in that manner. So the systems that we're interested in particularly are where you have quite a lot of vaporization. So if you apply, like I say, a very high energy density laser beam or electric arc, you actually vaporize the metal. So you get a much bigger volume of vapor produced relative to the amount of liquid that was vaporized. So you can't then describe that as being incompressible. So that's more like what we see in this picture here on the lower right hand side. So in that case, you would say that the divergence of the velocity field is actually bigger than zero. It's not incompressible anymore. So we did quite a lot of work to develop mathematical frameworks that describe that process while also capturing all of the physics that is kind of universal, whatever your assumption on the velocity field is. So the main ones for those are sort of the recoil pressure force and the Marangoni force. So they're like surface forces, and Marangoni force is normally kind of one of the dominant forces, and that arises because the surface tension of liquid metals is actually quite strongly dependent on temperature. So when you have a higher temperature in the middle of a weld pool, for example, you will get tangential flow across the surface of the whirlpool because the surface tension is essentially lower in the middle of the hot region compared to the outer region. So you get these, and that's called Marangoni flow. So if you drink wine, you get the same effects due to concentration in wine. People call it the tears of wine, I think. So basically, we've been developing these frameworks that describe this process. So and actually, it's really important because when you have these keyhole processes, so when you have these really high penetration joining processes that give you high throughput and increase your productivity, it's actually this vaporization that stabilizes that, what we call the keyhole or the thermocapillary. So you can see in this picture here is if you have a laser beam and we've got some sort of constriction starting in the keyhole, the laser beam will vaporize the portion that started to constrict. It will sort of bounce back, and that will stabilize that and will allow us to have that high productivity. So if you want to describe that mathematically, then you have to have these kind of advanced frameworks that we've been developing. And also it's useful, maybe people are wondering, well, why don't we just do the experiment? Well, actually, a lot of these phenomena occur far too quickly to observe experimentally. So we develop these mathematical frameworks that allow us to predict that behavior and optimize a process numerically so that we don't have to do an experiment or we don't have to spend a lot of money fine-tuning our parameters. So I'll not spend too much time on this, but this is basically what the framework looks like. So there's just some equations that describe conservation of mass, conservation of linear momentum, and conservation of energy. And as I say, we've got some novel aspects there because our flow is not incompressible. So these material derivative terms appear in our framework, which don't appear in other people's frameworks. So why is that of interest to anyone, I guess? Well, as I say, if you understand all of the physics at this kind of length scale, this continuum scale, then actually you can use these tools to optimize your process. So this is from some work that we did with the Nuclear Advanced Manufacturing Research Centre. So they are basically trying to get power beam welding into the nuclear codes and standards. And the problem with that is that although you get these really high penetrations and really high productivity with these joining processes, actually when you turn off that beam, as maybe was shown in that video, so we've got the keyhole generated, it's moving along a seam of a joint, then we turn the power off, the keyhole collapses. Actually, what happens more often than not when that keyhole collapses is you get a lot of porosity because either vapor porosity is included or gas porosity from the process. So we did some work with the NAMRC to try and numerically, and as I say, because an experimental campaign to find out the optimum parameters is prohibitively expensive. So we did this sort of numerical optimization campaign where we basically used this mathematical tool we developed, and we were able to go from this scenario where we had quite a lot of porosity in the weld to then choosing the power ramp down parameters so that then the keyhole collapsed very nicely. As you can see, there's no porosity in this weld, and this is some examples of how what we varied in this, and this is a paper you can read if you're interested. So varying the electron beam parameters to optimize for to mitigate against porosity basically. And what's nice again about our framework is, maybe I didn't specify this, is that because it's a fully multi-component framework, actually we for free we get predictions of the element evaporation losses. So actually what happens in these materials is the elements of the alloy that are more volatile, they evaporate preferentially. So actually in an SA508 steel is a known phenomenon that you get manganese evaporating preferentially, and we just predict that for free. So we can actually predict what effectively the different alloy that you'll get in your joint region. So that's another really novel sort of aspect of our work. And then obviously because the physics is universal, and that's the kind of novel, the nice thing about what we do, we can apply that to any system basically. So we applied the same framework, and this is on the left here just showing that we're mass conservative, another really important thing to have in continuum mechanics to conserve mass. So yeah, so we done some work applying this same framework to laser powder bed fusion processes. So again, just to say why are we different? So there are these two sort of approaches. So there's a simpler approach where we assume that the divergence of velocity field zero, incompressible, and we have our sort of full fidelity approach. And actually, we decided that it was useful to the community to make this simpler approach available, open source. So we've done that in a few tools. So we have released. Yeah, maybe it's worth comparing. So again, the simpler approach, there's just two phase, and our approach is fully multi-phase. And obviously we're resolving this vapor phase, whereas the simpler approach doesn't resolve the vapor phase. And then they have to apply what's called a phenomenological recoil pressure term, because they don't actually capture the physics of the recoil properly. And as you can see, our approach captures this really high velocity field, and that's kind of the main criticism of the other approaches out there, that the velocity field in the keyhole region is not captured properly. But we release these open source, so first one that we released was kind of aimed at electron beam welding applications, but is broadly applicable to a lot of things. And that's available, as I say, open source. We wrote a paper around that. And then the kind of like a more up-to-date version, I guess, but we did some work in applying actual laser ray tracing. So we have a version of this simpler the approach that describes the vaporization in a more simple manner is available open source, and but has now a ray tracing algorithm. So we discretize the laser beam. So this is really specific for laser welding applications, and it's important to have that ray tracing capability because what these, you might not be able to see them, but these are plots down here of experimentally observed plots of penetration versus time. And what happens in laser joining applications is that the surface of the weld pool deforms into essentially a parabola, and then once that happens, you get this very rapid increase in the penetration rate because all the lasers basically focused onto a much smaller point in the center. So you get this sudden massive increase in the penetration rate. And you don't get that if you don't have the ray tracing sort of capability. So we released this code, and here's just an example of this in action. So if anyone's interested in sort of laser powder bed fusion, laser welding, laser cutting, anything like that, this tool is available. And it's used quite extensively by industry actually. So it's used by, as you'll see in an example in a moment, Sintef in Norway. It's used by Airbus. It's used by the United States Air Force, DSTL. It's used by the United States Army. There's many, I could go on, there's sort of 20-25 organizations, industrial organizations that are using this code to optimize their processes currently. So, and that's not to speak of all the academic institutions that are also using this code. So it's a really successful tool that we've developed. And also I should say that, so this is using that simplification that the divergence of the velocity field is zero, as I say. That's actually quite a good simplification. So in a lot of cases, you can get away with that. What we found anecdotally is that actually you only need to sort of use the full fidelity description of the vaporization if you've got very large keyholes, so very deep penetration keyholes. That's when the sort of simplification falls down. And also we've released like a multi-component version. So if you're doing like powder bed fusion of dissimilar powders, for example, or a dissimilar laser weld, this is the tool that you could use then to simulate that. So that's the sort of update for the laser beam foam tool that we released. I've just shown some of the ray tracing there. And then, yeah, sorry. So just an example I thought was useful to show was that this is using that laser beam foam open source sort of ray tracing code. But actually, I thought this was useful to show because this isn't my work. This is actually from some researchers in Sintef in Norway. So this is using our code that we released open source to the community to actually look at optimizing aluminium laser welding and laser powder bed fusion of aluminium. And actually, the experimental measurement and the numerical prediction of this porosity is actually pretty, spot on really. And also the keyhole sort of morphology is really well predicted by our open source tool. So as I say, I didn't do any of these simulations. These are just researchers using our code. So very happy with the sort of engagement from the community for this tool. And all of the stuff I'll be presenting on will eventually be released open source. This is just kind of the first one that we've released. So then the other area that I guess we've made quite a lot of progress, and this was the work we actually won that award for, was we developed a magnetohydrodynamics description that describes systems where so basically if you want to describe a system that has a varying electromagnetic field and also some velocity field that then sort of feeds back and influences the magnetic field, you need to have a mathematical description, and broadly these descriptions are called magnetohydrodynamics. And actually, we found that we wanted to use this to describe arc welding, basically. So we wanted to have a much better physical description of arc welding mathematically, and we found that there wasn't that description in the literature. So there were magnetohydrodynamics descriptions for systems that have constant electromagnetic properties, but actually in arc welding you have massive gradients in the electromagnetic properties. So the equations were not derived for those scenarios, so you couldn't actually describe the arc welding process properly. You had to use a simplification that's called the electric potential formulation. So we went through and we derived these equations that are shown on the screen. Again, don't want to go into too many details, but the long story short is that now all of the physics of the arc welding process or any electromagnetic process is fully described by these equations, and now everything is just a boundary condition. So before we did this, you'd have to kind of fit a surface Gaussian distribution heat source. And now actually everything's fully described. So it's really a really novel, really exciting way to capture all the physics and just to show that it's all validated. So we validated against some experimental. So these on the top are my sort of numerical predictions of a bubble trajectory, and on the lower portion is like an experimentally measured bubble trajectory, and also we validated to very high magnetic field strengths. So this is just showing there's actually 4 plots here. So there's 2 magnetic field strengths and showing that we reproduce the analytical solution, which is kind of the best. An analytical solution is the best you can get. Basically, it's a full description. I don't know what the word to say is. It's the gold standard of validation is an analytical solution, but they don't always exist. So this is just to show we capture that. And yeah, so why is that of interest again to the foundation industries? I guess, like I say, if you are doing an arc welding process, then this is the tool you would need to describe that. So we were the first to kind of predict and experimentally observe this kind of interesting formation of structures in a dissimilar weld, which would ultimately affect the properties of that weld. But this is broadly applicable. So we did some work with the Royce Institute with the application scientists to look at the heating around a plasma torch that could be used to melt glass. So in the glass foundation industries, you might be interested in this work for that reason. So this was really fundamental work. So we were looking at the stability of a plasma plume due to the applied velocity field and magnetic field strength and current, sorry, which generates the magnetic field around the electrode of the plasma torch. So we basically saw, as you might expect, but still it's interesting that with a lower applied gas velocity, we get sort of magnetic reconnection with the boundary of this plume. So that would be an inefficient heat transfer mode, whereas with a higher velocity, you get more efficient heat transfer. So basically, what I was trying to say with this is that we capture the physics sort of fully. That's our sort of USP. We kind of go to the extra fidelity in terms of the physics and the mathematical representations, and that gives us the benefit that this work is then broadly applicable to all sectors. So it's really, really works really well, I guess. So then I guess that's all I wanted to speak about the thermal fluid dynamics. The next sort of work, and I'll try and go through it a bit quicker because I guess I've run on a bit, is the microstructural modeling. So basically we use a technique called the phase field method, and that's good because you capture all of the interface and bulk physics. There are simpler approaches called the cellular automata or level set methods, for example. They don't capture quite capture all of the physics, but we use this higher fidelity method. Again, that's like a theme in everything I'll be saying, I guess, that we use higher fidelity methods. And that's what we do in our group. So again, not to sort of bag on about the maths and everything, but it's really new, really novel, and we fully describe the system. And the main thing that we do is we have to describe the free energy of the system. So we fit what's called a Gibbs free energy to a polynomial expansion, and then that allows us to describe any system that behaves in a substitutional manner. So this is really good for things like solidification. We're actually working on implementing another sort of form of this for interstitial chemical components. And again, what we've done that's really novel is fully capture the anisotropy of the system. And that's important because when you have solidification, if you've seen these sort of dendrites that form in metals, well, you have to capture the interfacial energy anisotropy and able to properly predict those dendritic structures. And actually, no other phase field formulation has done that. We're the first to sort of fully capture that that anisotropy, and that allows us to predict these really nice sort of microstructural evolution animations, basically. But this is looking at the sort of coarsening in a heat affected zone of a titanium 6-4 alloy. So the color is like the temperature, and then you can see the microstructure. We actually had some pinning particles in this microstructure, and what we're trying to investigate here was the effects of the thermal properties of those particles on the evolution of the microstructure. And as I say, so not too much on this because it's just some math, but the reason that what we've done is so different is because we've actually gone to the effort of doing this. So this is called the variational derivative. So this tells you how you get down the free energy landscape, and this is what you're minimizing in the phase field method. Actually, this first term here, this divergence of the derivative with respect to the gradient, well, when you have these gradients to the power 4, that becomes really tricky. And this is the result of that. So we're the first people. So I went through this and did this analytically. So we have this in our code, which again is going to be open source probably by Christmas, I would have thought. So you can predict these, you can run this code, and here are some examples of our code sort of in action. So what we have here is some crystals, so some solid seeds, I guess, on the boundary, and then they're allowed to grow. And as you can see, so in this case, in the top left, we have no applied velocity field, and that's the other thing. We sort of have the flow through the dendrites in our code, in our mathematical framework. So the crystal that's sort of preferentially aligned with the domain that grows sort of obviously preferentially. This one in the middle is kind of rotated 90 degrees, and this one's rotated like 45 degrees. This one's rotated 22.5 degrees. And actually what you see is that when you apply different velocity fields, and it's all very complicated because you get solute redistribution, so there's two competing things going, depending on the temperature, that sometimes the dendrites grow into the flow field, sometimes they grow away if they're driven more by solute redistribution. But you can see here that the flow, basically what we're showing here is the flow has an effect. So as you increase the flow velocity, so this it's a bit difficult to see, but it's sort of going from the top left, top right, bottom right. So as you increase the flow velocity, basically you get the dendrites bending over more, and actually that can influence that. Well, the hypothesis is that could influence the texture that you see in the sort of joint region or the solidifying region. And then also we've done work, and then again, this is a simplification. So we're probably going to release this code, although if we release the higher fidelity one, maybe we'll not even bother releasing this. But this is another work in progress that we're hopefully going to release soon for the community. And this tool would allow you to have so this simulation has the ray tracing plus the evolution of the microstructure. So again, solving a slightly different set of phase field equations, slightly simpler phase field equations, but having all the thermal fluid dynamics in there and the solidification. So very powerful tool, quite computationally expensive, but you get a lot for that computational expense. And then finally, very briefly, the final area that we've very recently got into is looking at solid mechanics. And people, so the word Eulerian, I think, came up in the introduction. So what I guess there are two approaches to continuum mechanics, there's a Lagrangian approach and a Eulerian approach, and you can have sort of it's a spectrum, because you can also have Eulerian, Lagrangian, mixed approaches. But basically, a Lagrangian approach, your mesh, the way you numerically discretize your problem, that moves with your solution. And in a Eulerian approach, the box, your mesh, is fixed, and your solution moves through the mesh. So so you will have seen Eulerian approaches in everything I've done so far. So they are like fluid mechanics type approaches, where your fluid flows through your mesh. And if you've I won't show any Lagrangian approaches, but if you've seen any solid mechanics, you've probably you definitely have always seen a Lagrangian approach, where your the mesh that discretizes your part moves. So you apply a load, your mesh deforms, and that's your part deforming. And that's normally beneficial for solid mechanics problems, because the strain is proportional to the gradient in displacement, so it makes sense to formulate the equations in that way. But actually, what happens if you have very high strain rates and very high strains is that the mesh can become so deformed in a Lagrangian approach that the computational points, or the elements where you sort of solve these equations, can basically sort of smash through each other, and the mesh can be so deformed that what you would see if you ran that solution was that people would say the solution blew up, or the code failed or something. But actually what it is that when the code tries to take the spatial derivative to solve these equations, it basically returns an infinite number, because the mesh has actually gone through itself. So actually, in those approaches, it's much better to use a Eulerian approach. So we've developed these Eulerian approaches for plasticity, which are really novel. Like no one's doing this, because of various reasons. It's expensive, and it's difficult, basically. But what it means is that we can now solve these very tricky solid mechanics and solid dynamics problems, where you have very high strains and high strain rates. And again, not to dwell on the maths, but solving the same equations, basically, but as all the fluid stuff. But now we have this additional complexity in that the solid that we're interested in is metals, and metals deform on slip planes. So it's the slip systems in the crystals that we have to solve for. So again, there's going to be a lot of equations, but please don't worry about it. The main thing is that our polycrystal microstructure moves through our mesh. That's essentially what I'm getting at here. So and this is useful because if you want to know how your material fails, so where does stress localize, where does plasticity happen in your microstructure relative to the different orientations between the crystals and the slip systems within the crystals, then you need this approach. So there are many crystal plasticity approaches out there. They're all Lagrangian, and they're all only applicable at sort of low to moderate strain rates. If you want to look at really high strain rate systems, then you need this Eulerian approach, which we've developed sort of in the last sort of few months. And yeah, so it's very much more complicated in certain ways than the Lagrangian approach, because now you have to advect all these fields through your computational domain, which is expensive. But we found sort of novel ways to do that. So again, the intention is to make this tool open source. Again, longer term, probably it's quite a lot of work to make these things open source, as people probably understand. But again, yeah, a lot of equations, pretty dull, really. But here's an example of it going on. I guess this is what might be of interest to people. So so we have this initial microstructure here on the left hand side. We apply some shock, and what you're seeing is the sort of shock wave propagating through that polycrystal microstructure. And bouncing back off the domain, and then we're getting some localization of strain. So here is, for example, where you would get more plastic deformation in this region here, this band that aligns with this grain boundary. And also, because we fully solve all of the physics, we get sort of local thermal increases, local temperature increases due to that localized stress. And the more up-to-date version of the code actually has like thermal softening, so we can predict things like adiabatic shear banding. So I guess this work would be of interest to anyone in the metal forming sector. So if you do high strain, what's it called, die casting, I think. You squash your metal, basically. You wanted to understand what effect that had on recrystallization. This was the kind of tool that you'd need, because there's no other tools out there that do this. So basically that's my talk really. So I think what we are doing at Manchester is developing the highest fidelity mathematical descriptions of metals, glasses, anything that you can describe as a continuum. That's our work. And we've sort of captured all of that physics in the thermal fluid dynamics and the solid dynamics. We've made a lot of progress, a lot of industry engagement, and it's proved to be very beneficial to those industry sort of people who have engaged and have sort of either funded the work or they've just benefited from the open source tools that we've put out there. So we're doing a lot, and we're really strong on open source. So it is quite a lot of work to get stuff open source because all the documentation you do for so that people can actually use it. But the goal is to make all of this open source in the next, well, I don't know really. Application scientist, the Royce sort of framework that's available. But yeah, so we've developed these tools. They're proven to be much better than other approaches that are out there, and we're just carrying on really. So we're just trying to build up the team and get people using them and get people looking at different systems and different interesting things really, and then develop things further and sort of couple everything. And ultimately, what we're going to have is one tool that actually does everything and captures all of the physics in one robust mathematical description. So already the crystal plasticity tool, you can see that some of those phases that we call them in the code, they could be different states. So you could have liquid, one of those phases could be the liquid and solve the equations differently. So we already know the way forward, but it's all really exciting, and we're just happy to keep going really. So thanks very much for your attention, and really happy to take any questions if anyone has any.
Thank you, Tom. That was quite exceptional. Thank you very much. I will not profess to understand all of it by any stretch of the imagination. There's an awful lot of maths there, but the outcomes are absolutely amazing. So congratulations for the research. It is
Thanks.
truly exceptional. So and it's marvelous that you are trying to make it open source. I think that will give tools to the community that they sorely need. So I'm going to open the webinar for questions, and we're going to try to do the raise hand, and that means I'm going to have to find the participants, which are in a different section. Okay, so we have Samuel, who's raised his hand to ask a question. Can you go ahead, Sam?
I think, Sam, you need to unmute if you can hear us.
Oh, sorry, I just mispressed it. Sorry.
We can hear you now. Oh, we could hear you.
Yeah, I just mispressed the my Zoom is acting weirdly, so it keeps raising a hand by itself. I'm not sure why.
Okay, so you don't have a question. Apparently not. Okay, fine. So I'm going to ask this. I'm going to. Oh, Bill. Okay, I mean the chairman's prerogatives to ask a question when when things are quiet. But we have a question from Bill Sampson.
Yeah, thanks, Tom. Really, really good. Really nice to see this work developing. I've got a couple actually, but I won't hog it. The main thing I'm interested in is that a lot of and you've got some really, really beautiful simulations there with some really nice agreement between experimental and the simulation work. But it's all qualitative. And I wonder, are you looking at quantitative comparisons between experimental and simulation, or is that, well, yeah, you can answer that, I guess.
Yeah. So I think so. I didn't show it in the talk. Actually, in some of the papers, you'll see very quantitative comparison. So and actually in the paper by Sintef as well. Actually, that's quite recent. But that there's some really quantitative comparisons. So they did these process parameter maps and actually showed incredible agreement between the laser beam foam prediction and the tool. But basically we always do quantitative validation and verification. Yeah, for sure. Yeah, it just doesn't make very pretty figures normally. That's
And if I can have a second, Chair.
Yeah.
So when you did these the dendritic growth and you were in the flow space, and I wondered how sensitive are the structures that you get to, presumably there's some sort of random seed going on in that. How sensitive are the structures that you get to the random seeding that you use?
Yeah, so in we didn't actually use a random, so in that simulation the orientation is actually set of the crystals, but yeah, definitely if you were to do like a microstructure, you'd use some kind of random, and I would imagine it would be very sensitive to that, because obviously the crystals that are more in line with the preferential growth direction, which would be influenced by the flow and the solute composition that's been kicked out of that growth interface, would be, yeah, they'd be very sensitive to that, so it would definitely have an effect. And I guess you'd have to do many tens of thousands of grains to kind of average out that sort of sensitivity by yeah.
Okay, thank you. Cam, you have a question.
Hi, Tom. Really interesting talk. I really enjoyed that. You mentioned high fidelity a lot during the presentation. I guess I'm not a modeler, but high fidelity I would also equate with sort of relatively slow as well. So I was just wondering how you manage that.
Yeah. So for sure, like the stuff we do is I describe it as computationally expensive. So and that's actually the reason we sort of went to the effort of doing the lower fidelity stuff, I guess, and because it's, as it turns out, yeah, there are definitely some applications where you can use the lower fidelity work, but I guess what we were trying to do, and my experience has been that so during my postdocs, a lot of people they were doing like weld modeling simulations using just like a heat conduction analysis, and basically they were running that lower fidelity simulation like 500 times because they were always having to fit something, and then something else was, oh no, that's not quite right. So actually I think my opinion is that it's better to have the computational cost, and yeah, maybe it takes, so some of those simulations took like 2 months to run. I'm not going to try and sugarcoat that, but that's 2 months, and then you get all of the results or all the answers that you're looking for because you've kind of captured all that physics. I think you, on the flip side, if you were to use a lower fidelity approach that then neglected something, actually, you probably get the result and actually it's not, it's not right. It doesn't agree with your experiment or whatever, because that thing that you neglected that made it quicker actually turns out, in more often than not, to be quite important.
Yeah. So you can get the wrong answer fast, basically.
Yeah, exactly. Yeah.
And you kind of touched on this in your answer, actually. But are you identifying those areas by doing this detailed work where you can save yourself time and not sacrifice too much detail?
Yeah, that is work we're doing, but it's kind of not been as expert. We've got a few projects currently where we're trying to benchmark essentially, the higher fidelity version. Like where is it in that space that the high fidelity version is needed? So far we've definitely seen it in, just like anecdotally, we've seen that in, so for the NAMRC we were doing these very deep penetration welds, for example, and in that case the simpler approach just fell out. It just didn't predict the right morphology of the key, whereas the high fidelity version of the approach predicted everything sort of, bang on. But I know other people, like the Syntef work, they've used these quite small keyholes, and they found that actually the simpler approach works fine. So I think there's some work needed there to kind of try and actually like Bill said, quantitatively say where the different approaches are necessary, because currently it's kind of a bit hand wavy, I guess. But definitely that's the way we're going, because as well, one of the things, so a lot of you'll see a lot of stuff that, and I'm not, it's not, other people who do this kind of work, they might say, oh, that's, we use this simplification, and actually the reason is because it's actually really hard to not do the simplification. But our approach is kind of get everything in there, and then only then can you say what you can take out, because only then can you compare, because you've done the harder thing in the first place.
Okay. Yeah, that's clear. Thanks very much, Tom. That's
Thanks. Yeah.
Exciting and good for us to know, I suppose, where, if we're doing sort of fag packet calculations, we're way off or a little bit closer. That would be helpful for the non-modelers in the room.
So, I'm going to use chairman's prerogative and ask a question, if that's okay. I think what you're doing is fantastic, and you're clearly intent on getting it all open source. And you're looking at metals primarily. You've hinted that you've stated that you're doing some work on glass. What do you see as the next steps for what you're doing? Are you going to apply what you've done to other materials? Are you going to make the models more sophisticated? What is the next stage for you and your development work?
Yeah, so I think there are there's kind of so many different avenues we could go down, but for sure one of the things is to apply to different systems. So if you had like plastics and things, like if you were interested in so that would just be a different so how do you relate the strain in the system to the stress in the system? It would be that simple to kind of
which may be partial in many cases.
Yeah. So there's that. There's applying it to different materials, but then also what I'd like to do is kind of fully couple everything. So currently, for example, if you with that solid dynamics work, that's kind of separate. It's like its own little entity. We have this microstructure, but actually that should be integrated within the phase field framework, so that you could do something where you applied like a thermal load, so you get the coarsening of the microstructure, and at the same time you get the stress developing. So if people are interested in like residual stress in any kind of system, you'd want that kind of description where you could resolve the intergranular stresses and the intragranular stresses, and then on the bulk that would give you the residual stress in the system. So that would be very powerful, because then that would be actually a complete description, and that we could do that because of all the work we've done and how the codes are all set up. We could really do that in a few days if we wanted to. It's just we've not really published everything we've done so far, but then that would be kind of the best you could do in that particular area. But I think we'll always find different avenues to explore. There are so many different ways we could, and also like in the thermal fluid dynamics work, it's like how do you describe a gas? What kind of equation of state? There's loads of different avenues to go down. Even just a lot of people spend their careers on one of these areas. I think we're going to try and sort of do all of them, and then that's why we want to make it open source, basically, so then people who contribute and work with us.
I'm going to ask a naughty question. There's always a nice naughty question at the end of these things. So your transition of state is mainly at the moment liquid to solid. Yeah, that's what you're focusing on. But there's many other transitions of state, such as an order disorder transition in a ferroelectric, for example, or a displacive transition in a ferroelectric. So these kinds of transitions of states, they have a level of crystallization, which is ferroelectric domain formation, for example. Do you think you could modify what you're doing to move in those directions as well?
Yeah, definitely. Yeah. So that's the way we see. So that's the, like, I guess in the phase field type frameworks we're doing. So what all you need to do, well, I say all, it would be difficult, but you describe the system as a free energy. So the free energy of the system, and we're minimizing that free energy. So currently, we have like the chemical contribution, the interfacial contributions. You just have to have a mathematical description for what that free energy was, which would be you'd be able to get that from thermodynamics. So, and then that would just go, you just take that through the the calculus that we do, and then that would come out in the result. So for sure, that is where we're going, because already we have this interest in magnetohydrodynamics. So if we apply we add the magnetic contribution, then we can look at what does a magnetic field do to, as you said, we're interested in metals, but you could easily apply that to any state transition of any material. And there'd be obviously a lot of complexity there, but broadly speaking, the approaches that we're using could be applied to any system. Yeah.
Okay, thank you. I may be talking to you in the future about those kind of ideas.
Yeah, brilliant. Yeah, please do. Yeah.
It's my personal research in many ways. So, I'd like to thank Tom. Just see if there's any last questions before we end the webinar today. Neil, do you have any comments about the availability of the talk and so on that you want to make?
Yeah, so we will publish the presentation on our YouTube channel, so we'll make that available. And if Tom's happy to give us a copy of the slides, we can make those available on our website as well.
Yeah, definitely.
Are we sure all those videos are going to work, Neil?
Yeah, they should do, yeah.
Right, okay, that'd be good. So Tom, thank you very, very much. That was really enlightening. It's nice to have somebody reasonably close in Manchester doing this kind of work. I think I will be talking to you in the future.
Yeah, thanks very much for having me. It's been really, really great. Thank you for all the questions. Yeah, really interesting.
And it's nice to see somebody young who's got some new ideas and has new approaches that are moving things forward in a traditional industry.
Yeah,
It's not a traditional industry by definition. It's been around an awful long time. So thank you very much. And I don't think there's any more questions, so I'm going to conclude the webinar for today. Thank you.
Well, thank you. Bye.